Alright guys, today I'm going to go over chapter 4, section 5, and chapter 4, section 6 notes. I'm at home, so my microphone is not working right now for this, I don't know, with this computer, so bear with me, I know it sounds a little funny. So on section 5, we're going to start out talking about isotopes, and this is a term that we'll see throughout the year. And we don't always talk about it, so kids a lot of times forget what it means, or that it's really easy to forget what that means. But it means that it's an atom of the same element, and they have different mass numbers. So, for instance, we'll look at carbon here in a little bit, and maybe it is, I have a carbon atom in my right hand that weighs 12, and maybe I have a carbon in my left hand that weighs 13. And I've said this several times in some of your classes that the mass numbers on the periodic table aren't really truly the right mass number. It's just an average. So we're going to look at that. So electrons, protons, and neutrons, which one can change from the notes that we've done? The ones that can change are my electrons. I'm going to do this here. And my neutrons can change. And then it says electrons, protons, and neutrons, which ones have a weight? Well, if you remember back from the previous sections, electrons pretty much don't have much of a weight. So we just kind of look at them as having 0. So my protons weigh 1 AMU, or we'll look at that as like 1 gram later on. And my neutrons weigh 1 AMU, or atomic mass unit. And eventually we'll switch those into grams, so we'll just call them grams. Alright, the third bullet point here. So which subatomic particle is changing to make an isotope? Alright, so looking at this, I know that electrons and neutrons can change. Okay? My protons cannot change. The ones that have a weight are protons and neutrons. So if my weight's changing, which one of these two is changing, my protons or my neutrons? Well, my protons cannot change, so it has to be my neutrons. So let me do a text box here. So it would have to be neutrons there. Okay. Oh, here we go. So change that to neutron. Alright, so a nuclear symbol is what we have looked at before. It looks very similar to like when we just see it on the periodic table. So the nuclear symbol, it says label the mass number and the atomic number. Alright, so the bigger number is always going to be your mass number because that is protons plus neutrons. Right? This smaller number is always going to be your atomic number. Your atomic number is how many protons you have. So if this is protons plus neutrons, it's going to be bigger. It's almost always going to be bigger. Alright, so the information I can get from the nuclear symbol. What I can get from this, I kind of talked about a little bit, are my protons. My protons are 11. Not Q, 11. Alright, my electrons are 11, and that's because right now I am looking at a neutral atom. We'll eventually look at some that aren't neutral in another chapter, but right now it's a neutral atom, so if I have 11 positives, I'm going to have 11 negatives. Now my neutrons, I'm going to subtract 23 minus 11. That is going to be 12. So I can get all that from this nuclear symbol. So let's go down here to the learning check. Naturally occurring carbon consists of 3 isotopes. Now remember, an isotope is the same element but different weights. So state the number of protons, neutrons, and electrons in each of the following. And also, before I do that, not only is an isotope the same element but different weights, it means that neutrons have changed. Right? Protons didn't change, neutrons did. Alright, so for protons, for carbon 12, I'm going to do carbon 12 first. I have 12, which means my electrons are going to be 12. It's a little hard to see there. 12. Now carbon weighs, or its atomic mass is 12. It's, oh, sorry. I did not put its atomic number up there. So its atomic number I forgot to put should be 6 down here. And I'm not really for sure how to do that on here because I don't know how to do a superscript and a subscript at the same time. So carbon is 6. So if you want to, right here in this little bitty spot here, there should be a 6. So if you want to try to add that on your paper, you can. But on each one of these, there should be a 6. Alright, so 6 protons, 6 positive protons, 6 negative electrons. So I'm going to take 12 minus 6 to get my neutrons, and that is going to also be 6. Alright, now for carbon 13. My protons are still 6. If my proton number changes, if it now is like a 7, then I am no longer carbon. Alright? My atomic number tells me the number of protons I have. So, no matter what, my protons are staying the same, and so are my electrons in this case. Now I'm going to take 13 minus 6, and remember I said an isotope. Neutrons are changing, and it is 7. On carbon 14, my protons are still 6, which means my negative electrons are 6. 14 minus 6, though, is 8. So my neutrons have changed. So like I said, every time if you have an isotope, it's your neutrons changing, and that's how your weight and your mass are changing. Alright, so learning check. Write the nuclear symbol for the atoms with the following subatomic particles. Alright, so if I have 8, 8, 8, 8 is going to be oxygen. So I'm going to put an O there. I'm going to try to get, oh gosh. So, okay, before I even do the oxygen, I'm going to try to do the superscript above. So that's its weight. And the weight comes from protons and neutrons, which 8 plus 8 is 16. Alright, so I'm going to do my superscript, and I'm going to write 16. Now I'm going to put oxygen, and then I'm going to try to do another little text box right here with an 8. I don't know if it's going to let me move that up or not, but I'm going to try. There we go. Alright, so that's what it should look like. 16, 8 on bottom, and it's oxygen. Now for B, I'm going to have to, what's that, 30, the weight is going to be 37. So I'm going to do a superscript, do 37. Now, if you're not sure how I'm figuring out what element this is, I'm going to go to a periodic table. Let's just pull one up here. And if you look at 37 on here, that is rubidium. So I'm going to put RB. So that is, well, the weight is 37. I'm sorry. This one does not have weights. Periodic table, no weights. Let me try to find a good periodic table here where there's weights. Well, guys, I'm just trying to find an easy one where I can read the weights quickly. Oh, my goodness. Alright, well, here we go. There's weights here. Okay, and my weight was 37. So I'm going to look for the weights here. 37, 37. And it looks like, trying to read this, there's none that are 37, so then let's look at my proton number. My proton number is 17. So that's the easier way to get it than the weight. 17 is going to be chlorine. So I'm going to write Cl, and then I'm going to try to do what I did before with the oxygen. I'm going to write 17. I'm going to try to drag that up here. Alright, so the weight is 37 because my neutrons plus my protons. My protons are my atomic number, so 17. And 17, that's how I found real quickly that that's chlorine. Now for the C here, the weight is going to be 107 because of my neutrons plus my protons. So 107. And my protons are 47, so let's look up element 47 on the periodic table. That is silver, Ag. So I'm going to Ag, and then my proton number is 47. I'm going to try to slide that up right underneath. Close enough. Alright, so that's what it would look like for C. So I've got A, B, C, and we're just writing what that would look like. Alright, the next learning check. Which of the following pairs are isotopes of the same element? Alright, so if it's the same element, remember they have to have the same atomic number. So that's what I'm going to be looking for. And then number 2 says, in which of the following pairs do both atoms have 8 neutrons? Alright, so let's just look at number 1 first. Different atomic numbers on A, so that can't be it. B, yes, they have the same atomic numbers, so they are the same element. C, atomic numbers are different, so that's not the answer. So it's just B for number 1. Now for number 2, in which of the following pairs do both atoms have 8 neutrons? Well, I have to subtract. So let's see here. 15 minus 8 is not 8. 15 minus 7 is not 8, or is 8. 12 minus 6 is 6, so it's not A or B. 15 minus 7 is 8. 16 minus 8 is 8. So C, the neutrons on this unknown element would be 8, and the neutrons on this second unknown element would also be 8. Emerson? Alright, sorry guys, this is what you get when I'm sitting at home. My daughter and my dog. Alright, I know. Atomic masses. Give the mass of an average atom. It's not the same as the mass number. Alright, so if you look at an isotope here, we have magnesium 24, magnesium 25, and magnesium 26. And they're just going off of the 3 different magnesiums that we find on Earth. Now, here's where I kind of tried to talk about this a little bit. I didn't go in too much depth, but magnesium 24, that is the most abundant on Earth at about almost 79%. Magnesium 25 we find at about 10%, and magnesium 26 about 11%. So what they've done, because we know, you look at the periodic table right now, there are not 3 different weights for magnesium. We just have the one weight. So how they came up with that one weight to put on the periodic table is they did this right here. They took the weight of magnesium 24, this 23.985, and they multiplied it by 0.7870 because that's what this is telling you. Woo, sorry. Let me do the markup here. This right here, well, won't let me mark anything up now. Okay, so this 78.70 divided by 100, that is going to be 0.78. So you're taking that times 23.985, and that's going to give you this 18.88. Magnesium 25, I'm going to take its weight and multiply it by the percent that we find it, and you get 2.531. We're going to do the same thing for magnesium 26. You get 2.902. I'm going to add these 3 numbers together, and I get 24.31, which is what they have on the periodic table. So that's how they came up with the mass number on the periodic table, and that's why I'm not too worried about us when we round these numbers, because they're already just an average anyway. So that's why it's not a big deal when we round the numbers and we don't use the exact number. Alright, learning check. Using the periodic table, specify the atomic mass of each element. Alright, so here, guys, you're just looking on the periodic table. So for calcium, calcium's number 20 right here. Let's see if I can get this larger. Alright. This is going to make this bigger for me, hopefully. Maybe, maybe not. No, okay, so anyways, calcium's number 20, it's 40.08. Alright, aluminum, if you look at aluminum, is 26.98. So you're literally just going through here and, oh, I can't get a new text box. You're just finding, and just finding the weights for these guys. So lead, if you look over here at lead PB, 207.20. Barium, if you look down here at barium, it's 137.33. And then the last one being iron. Fe is 55.85. And that's it for section 5. I'm going to go ahead and do section 6. And I'm going to have you guys get through as much as you can, get through what you can. But we have done some of this already. So each energy level has a maximum number of electrons equal to, okay, this is going to be 2n, and you can write this on your periodic table, 2n squared. I need to move that up. There we go. So, example, like if you're in that, remember that first initial circle that we had? That's energy level 1. So if I replace that where the n is, so if I write, let me put it right here. If I write 2 times 1, and then I square this, it's going to be 1 squared, 1 times 1 is 1, times 2 is 2. So this is going to equal 2, which is what I told you guys a while back. That's what that first circle holds. It only holds 2 electrons. Now if you look at energy level 2, if I do this, 2, and I square this one, and do the square, equals, so 2 times 2 is 4. 4 times 2 is 8. So that's how I know that second energy level is equal to 8. Alright, and then finally, I've got this one. Now, I just told you guys just to put 8 in the third energy level. But if you look at this, it's really 2. And then we're going to go 3. And we're going to square that 3. So 3 times 3 is 9. 9 times 2 is 18. Alright, once again, this thing right here is super, woo. Is that going to highlight everything now? Okay. This is super important. I don't know if it's going to let me highlight it or not since it's in the text box. No. But anyways, this one's right here is really important because now if you're in energy level 4, if we have to have a 4th energy level, you're going to take 4 times 4, because that's 4 squared, that's 16. 16 times 2 is 32. So it's not just 2, 8, 8, 8. Now that's what we're going to kind of use. This is what we're going to use as we go through it because we're not looking at the transition metals right now. So we're only looking at things that have 8 valence electrons. We're not going to look at anything beyond that. So valence electrons determines chemical properties of elements. Okay, they are the reason why things react. That's why things explode, or maybe they don't explode. Electrons in the highest energy level. Those are your electrons in your highest energy level. In chapter 9, they go into this in a little bit more detail, and I do not like how the book talks about it here and then does not explain it until chapter 9. So I've kind of moved chapter 9 up. We'll go over that more then. Are the same, valence electrons are the same as the group number of that element. So you guys have seen that. You saw where everything from hydrogen down had one valence electron, right? Everything, let me go here. Everything from beryllium down had 2 valence electrons. Now, when you guys made that periodic table, we did not mess with these transitions. Everything in 13 down had 3. Carbon in down had 4 valence. Nitrogen in down had 5. Oxygen, 6. Fluorine, 7. And then finally, your noble gases have 8. Although helium's different. It's only got 2. But that's what we saw when we did that. So, example, phosphorus has, let's look at this. Where is phosphorus? Phosphorus is right here. It has 5 valence electrons. So I'm going to write a 5 here. Alright, so what I have kids do every year is on your periodic table that you can have out and I let you write things on, I'm like, write 1 VE, 2 VE, 3, 4, 5, 6, 7, 8 VE. Write that on the top of this so you know that always, and just keep that in mind because that's going to be the easiest way. If I ask you, how many valence electrons does iodine have? I can go to iodine here and be like, oh, it's 7. I know it's 7 right away. I don't have to do electron dot diagrams. I don't have to do circles. I know it's 7. Alright, so learning check. State the number of valence electrons for each. For oxygen, well, let's go look for oxygen. It's right here. That is going to be 6 valence electrons. Alright, aluminum. If you look at aluminum here, it's going to be 3 valence electrons. Emerson. Chlorine is going to have 7 valence electrons. Okay, how do I highlight all that? Oh my goodness. Alright guys, I don't know how to... I don't know how to unhighlight that. It's wanting to highlight everything. Alright, so the answer is 7. I have no idea how to how do you get rid of that? Okay, there we go. Alright. It won't let me just highlight. Alright, it won't let me just highlight the 7. The answer is 7. And then calcium. If you look at calcium, it is going to be 2 valence electrons. So the answer is 2. It's bugging me that it won't let me just highlight this. I don't know. Alright, group 6A or 16. That's right here. That's going to be 6 valence electrons. And then finally, carbon. Let's go find carbon. It's right here. That is going to have 4 valence electrons. Once again, the reason we care about this is because those valence electrons, we're going to see in the next chapter, they're going to cause things to happen. Alright, and then last, electron dot models. Now, you guys did these already. There are the Lewis dots. So you're going to place dots above, below, or on either side of the element symbol. Like I said, they do not look like this in nature, but it's going to make your life a ton easier. The dots pair up, but not until they are on all sides of the symbol. So if you look at lithium, there's 1. Beryllium, 2. Boron, 3. Carbon. Now nitrogen, they start to pair up. Oxygen, you pair up even more until they're all paired up. Alright, and this is just showing valence electrons, and that is it. Alright, so it says write the Lewis dot structure for bromine. So what I'm going to do is I'm going to come over here to bromine, and I see, hey, bromine has 7 valence electrons. So I'm just going to do my text box. I'm going to BR. And then I need to put 7 dots around this thing. And I'm going to go 1, 2, 3, 4, 5, 6, 7. Alright, so I've got them paired up going all the way around. Alright, ionization energy is how hard it is to remove an electron. The harder to remove an electron, the higher the energy. Alright, so just think about that. Like, yeah, it's hard, it's going to take more energy. So when I'm standing by the board, if I'm standing at the board like I normally am teaching, who could I hold on to if I wanted? Well, if it's in third hour, I'm going to be able to grab a hold of Sierra, Carter, Grayson. If you're fourth hour, it's going to be Hunter and Avery. I'm going to be able to, like, I can grab those kids and I can hold on to them. I can kind of make sure they're not doing anything. Alright, so who could easily, though, on that second question, who could easily get away from me if I'm standing at the board? Well, if you're third hour, you're going to be like, gosh, the kids on the back, so like Lucy and Kylie and Mackenzie and Andre, all those back there, Emma and Zane and Carlin, I'm going to have a hard time keeping track of those kids, right? Like, I can't, if I'm up at the board, I can't really control you guys. If you're fourth hour, it's going to be Hallie and Kendall and Clayton and JC. I'm not going to be able to, I can't reach out to those guys. I cannot get you guys if I'm at the board, okay? So you can easily get away from me. So the same thing happens with elements. So I'm going to draw a Lewis dot diagram for lithium and sodium. Gosh. Let's do that here real quick. So basically what the ionization energy is those elements that have electrons on rings that are further out, they're going to have a harder time keeping track of those electrons. If you look at somebody like helium who has just 2 electrons and only 1 ring, 1 energy level, they have control of those electrons pretty good. But you get to elements like, oh gosh, like potassium, rubidium, or iodine, these elements that are down here on this part of the periodic table, the bottom half, they're going to react a little bit easier. They're going to lose electrons a little bit easier. Alright, which they talk about ionization energy in another chapter too, so we're not going to go too much into it. Alright, the same thing happens with elements. Draw the Lewis dot diagram for lithium and sodium. Alright, so for lithium, let's do lithium, and then over here I'm going to have sodium. Okay, so let's find lithium. Lithium and sodium both have 1 valence electron. Drawing. Okay, so I'm going to do my 1 dot and 1 dot. So these guys, they only have one electron. And then I'm going to draw a Lewis dot diagram for lithium and fluorine. So let me do my text box. I'm going to put lithium there. I'm going to draw fluorine here. Oh, drawing. Okay, there we go. Okay, so it's going to have 1 valence. Now, if you go to fluorine, fluorine has 7 valence electrons, so I'm going to put 7 around it. Alright, now if you look at your periodic table, all of these guys, they are happy with their 8 electrons. They're full. Their outer shells are full and they are not going to react. Okay, so 8 is our magic number. Unless you're hydrogen and helium, then 2 is your magic number. But 8 is normally going to be our magic number. So if you look at this, look at fluorine and look at lithium. Right now, neither one of them are happy. 8 makes them happy. That's the magic number. But can you see, do you guys see what could happen here? I'm going to do my select. Do you see where maybe, just maybe, I can do this? And just maybe lithium and fluorine can come together and make each other happy. Alright? Or maybe lithium just gives fluorine an electron. And fluorine's happy, and lithium's like, great, I didn't want it to begin with because it wasn't making me full. Alright, so anyways, this is what we're going to start looking at in the next chapter, is that kind of stuff. Alright, guys, that is the end of the notes. Let me know if you have any questions. Sorry, my brain's a little foggy right now, and this is taking me a little bit longer than I wanted to get through the notes. So anyways, let me know if you need anything, and I will see you guys next week.